So welcome back after lunch, everyone. My name is Daniel Brandell, and I have been invited to share this afternoon session before coffee, and we have three speakers. The first one is Professor Olexandr Isayev from the University of North Carolina, who will present on neural networks learning quantum chemistry. Please.
Okay, thank you so much. It's a real pleasure to be here, and thanks, Roland, for invitation for this amazing symposium. So, in my talk, we'll switch gear and mostly talk about neural networks and how we can use machine learning to accelerate quantum mechanical calculations. So I start with acknowledgement because it's always not enough time to finish. So it's collaborative work between my group at UNC, group of Adrian Royberg at University of Florida now, as a group of Sergei Tretiak at Los Alamos, and generous funding from ONR, NSF, and NIH, and a lot of compute resources by the various institutions. Now, I think this is why we're here, right? So we see this, chemical science is really attracted with machine learning. And, instead of doing rigorous way of quantum mechanics. So recently we published this a perspective in Nature when we have a look, kind of bird's eye view on application of machine learning in molecular and material science. And you can kind of think the type of application we do. And you can think about the several generations or scenarios. So, for example, type of the structure property calculation. And given a structure, we want to predict a property, right? And here we use some kind of local minimization algorithm. So when you run your favorite quantum mechanical package and minimize geometry, we typically do something like that. Then we can increase the challenge. And for example, given the composition, we want to predict the property. Here we use some kind of global optimization algorithm and the type of the problems like a crystal structure prediction. So given a structure of the molecule, can you predict the strict crystal structure? So this problem is still not solved. And you can think about the third generation when the statistical driven design. When given some kind of data that can be literature, text, wherever, so you can use machine learning to predict composition, structure, and properties. And then we also, in the paper, we did different methods and approaches to this problem. Now, in my lab, and what many other people doing. So when you run your QM package, you solve, for example, time-independent Schrodinger regression. And as you know, so this is second-order partial differential equation. So there is no analytic solution for anything practical. So instead, we rely on numeric solution of these equations. However, if you look on it from the point of view of machine learning, you can rearrange, and so your ground state energy would be some magic function with your input vector of your molecules. And basically, it's a regression problem. So what we do, we use neural networks, and we like neural networks because they're differentiable. So you feed molecules, you get energy. So then you can backpropagate and get gradients. So you have forces. So you can do geometry minimization, molecular dynamics, and all other properties. So for past couple of years, Adrian and I have been working on deep neural network, molecular potential. It's been, this paper with technical details, which actually use neural networks, and you can predict, and it's been trained on DFT. So why ANI? So this is ANI, and basically, given the proper training, basically what we want to do, we want to train the Padawan network become the DFT Jedi Master. However, unlike the original scenario, we want to avoid, so no one would be hurt in this destination. And also, when you look how convoluted we went with the acronym, and to kind of satisfy our nerdness, but also not to be sued by LucasArts. And basically, this is my flavor of these diagrams that Anatol showed. So if you have some kind of metric of accuracy versus the cost, and here is actually it's not a cost, it's a scaling of our methods, and so you can build this kind of a diagram. So if you're interested in running large molecular system like proteins, so you have to rely on some kind of classical potential or force fields because of this scaling. However, the problem with force fields, you cannot systematically guarantee their transferability, their accuracy, and sometimes these error bars can be huge, right? And so that's why, you have to rely on, rigorous quantum mechanics to, to get more higher accuracy. And eventually, would be nice to if you can run the protein with a couple cluster. So what we try to achieve in our work, so we pick a particular reference level of theory. In our case, it's range-separated hybrid, omega B97X from Martin Head-Gordon group as our choice. So we publish the ANI1 potential. Then we improve a little bit and show the technical details how you can use active learning to be much more data efficient and improve transferability of your potential. And more recently, we also use a couple cluster as a reference theory, and then you can crank up accuracy a little bit. Now, so neural networks are not magic. So what we do in our way, so we transform Cartesian coordinates in so-called local atomic environments. So it's a whole idea proposed first by Bell and Parinella 10 years ago. So in our work, we use slightly different mathematical expression of the form, but the idea is the same. So you split your molecule into this atom-centered environment. Each environment passes through a neural network, so you get this kind of fictitious local energy of the environment. And you train it, you sum them up and train to a total QM energy, right? So with neural network, you train them by backpropagation. Basically, you compute the cross gradients and update the network parameters to minimize the error. So basically, you run it many cycles. So in our work, we're interested into not molecule-specific potential, but more transferable. Ideally, for any molecule, you can draw and run. So it comes with a cost. Those things are extremely data hungry. So if you're interested, all these data sets are available, and basically there are about 25 million QM calculations for small organic molecules. Again, so to use to get those structures, we use GDB database, explicitly enumerated small organic molecules. In our case, from white 1 to 8 heavy atoms. And again, since we're interested in potential, so we use out of equilibrium geometry and bulk of this data actually, not the minima, but of the equilibrium geometries that's been generated with the normal mode sampling. Run. Then you train, you test on some separate validation data. However, there are a couple of ways how you can test it. So the typical way how it's done in the computer science, you're interested in interpolation, right? So if you train your system to 8 heavy atoms, you test on a different system with the same size. However, as a chemist, this is not very interesting because we're looking into some different types of molecules, larger. So I argue that for us, the testing on unknown sizes, so larger system, would be more practical for a, for a realistic, research scenarios. So what we developed the set of benchmark data sets, and here just to show you a distribution of molecular sizes. This is the heavy atoms. This is total number of atoms. This distribution in blue, this distribution of moleculars in our training data. So basically, it's less than 10 heavy atoms. And then we have this extensibility data set that's been drawn from some real, world molecules, for example, approved FDA drugs and some small peptides, but actually probes to much larger molecular sizes, wasn't 100 atoms. There are a few examples of those drug-like molecules. So you see typical, polar, non-polar molecules. And we also include a couple of these more challenging examples, like small proteins, where I can afford to run single-point DFT on them. So we put a couple of those proteins, and they are a few hundred atoms in sizes. Now, one of the critique when you develop those machine learning methods are or not only critique, but how we can trust them and when we can trust them. And one of the approach is to use active learning. And one of the simplest way of the active learning is use query by committee or ensemble disagreement. So just to briefly show you what it is, imagine I trained several neural networks, and I made the prediction in a particular phase space. Well, you can see there are certain regions where this prediction agree, but also there are regions where they disagree. So we can do then, since they are small organic molecules, you can go back to QM and run QM calculations. And now what we and some other people, and many other people show that actually, for many cases, when those predictions agree, typically we have a good data coverage. And in this phase space where they disagree, basically we either have overfit or a bad data coverage. So you can use this approach essentially without running any QM data, just looking at the ensemble disagreement to pick your next training molecules. And what it allows you to do is actually fully automated framework how to parameterize those ML-based potentials. So you can essentially throw a kitchen sink of all the data you can think, and you can train the ensemble of this neural network, and then you score and rank all your data, and calculate this disagreement. So then you batch and run them on your HPC resources, update the database, basically retrain your ensemble, and basically this loop is almost fully automated. So in contrast to training and refitting your standard classical force field types, which requires a lot of manual work, updating those machine learning parameters, potential in general, is almost fully automated. And again, so this work been published in this special GCP issue that Anatol mentioned this year. Now, in addition to fully automated training, basically active learning allows you to be much more data efficient. So when we publish, so what's this figure show you that on our realistic benchmark data set, original ANI1 potential that had been trained to very large number of molecules, but we selected them. Essentially, it was a random selection. And the transferability was not very good. So the RMSE and error were around 12 kcal per mole. However, if you do a data selection through active learning procedure, and so let's show you data size, basically by the point when you selected at 2 million data points, you already can match this accuracy with 10x data reduction. And you can go on. And by the 5 million data points, you essentially lower this error fourfold. So it's more accurate, and it's much more data efficient. So I think if you do training of the potential like that, and if you do random sampling, you should definitely have a look on that. So basically, what we see is universal improvement into accuracy of the energies, forces, and for every benchmark you can think of. Now, since we're interested in molecular simulations, the type of the quality of forces, what you can get, just to give you a perspective. So this is keep in mind. So this is a log plot of density plot. So essentially, all the points here in red of the forces from the force field versus the reference DFT forces. So you'll get the accuracy of roughly RMSE about 4 kcal per mole per angstrom, and basically the accuracy of those forces are very favorably compared with even semi-empirical methods like density functional tight binding and PM6 that have 2 and 4 times larger errors. Now, in addition to energies, we can predict different properties. For example, what we also worked quite extensively this year, we can predict partial atomic charges. You can predict, standard schemes, like CM5, Hirschfeld, or natural charges. However, we ask neural network a question. Since those charges are not physically observable, and I can have a look, because so this plot gives you a correlation between different charge schemes, and you can see, depending on what your scheme you use, basically those charges can be all over the place, because this partitioning is arbitrary depending on the choice of the particular scheme. So what we did in this paper, however, molecular dipole is physically observable. So if we ask a neural network to reconstruct a dipole and learn charges by itself, so that these charges would reconstruct computed QM dipole. And so basically that's what we did. The neural network, predict your dipole, and also partial atomic charges that would make this dipole. So we constrained only to a molecular dipole. What is also interesting, it gives us a very high accuracy in prediction of quadrupole. However, we didn't constrain them. But also what's interesting, so we called our scheme, charge scheme ACA. It actually closely resembles the CM5, charge model 5 scheme that was fitted to experimental dipole. And basically, this is one of the way you can reconstruct those dipoles. However, here it's unbiased because we didn't fit to any empirical data. Now, when we have these components, what it allows us to do, now we can do everything with machine learning. So I can run, for example, I can run my molecular simulation with machine learning, predict charges, reconstruct the dipole, and then, for example, I can compute IR spectra and everything with MD. So here is a couple of examples for some of the drug-like molecules. When we run time domain machine ML MD simulations, and this comparison with QM, and you see there's a very nice correspondence between machine learning and QM, and also very nice accuracy of dipole moments as well. Now, as been referred by several speakers this morning, sometimes what if we need accuracy beyond DFT? So what we've been looking at how we can run couple cluster simulation on a scale, because those methods are data hungry, and if you do conventional couple clusters, it's simply too much to compute, and it's way too expensive. So we were looking for approximate couple cluster calculation. However, to really get the high accuracy, you need to do your computation and the complete basis set limit, and the total complete basis set energy would be this CBS Hartree-Fock piece plus MP2 plus this correction for so this is standard Helgacher type extrapolations. So what really kills you this conventional couple cluster term, which is extremely expensive because of this 0.7 scaling. So what we are looking is to replace it with the approximate couple cluster. And again, so we have this extrapolation inside extrapolation scheme when we use this DLPNO, approximate couple cluster, and again, so which has a couple of different parameters. So what it allows you to do, so that's accuracy of the conventional CBS, and so this is the CBS with a star, which we replace conventional couple cluster with approximate, and you can immediately see, for example, the compute expense for aspirin, which has only 21 atoms, is more than 400 hours just to do the single points. However, in the approximate scheme, basically you reduce it to 50x. And as you can see, for the energy deviation for the couple of benchmark data set, basically you're not losing much of the energy. However, you really gain in the compute. So what we did next, now we have the way how to run high throughput couple cluster calculations. And now what we did, we use ideas called transfer learning, because we already have very nice data set and trained neural network with the accuracy of DFT. And it would be stupid not to use it, not to take advantage of all this data. So what we what we decided to do, so for example, what you can take your DFT trained neural network and copy all these parameters to your couple cluster neural network. Then what we did, we fixed a couple of layers. And so you retrain only part of the parameters of your neural network. And now you train on your couple cluster data. And again, we use a couple of cycles of active learning. And now you have kind of a Frankenstein models that have been trained part of the DFT data and then retrained with the couple cluster data. However, what we show in many cases, and I show a couple of benchmarks, it actually exceeds the accuracy of the parental DFT methods in some cases. So one of the challenging examples for DFT, for example, reaction energies, or for example, if you take this cage hydrocarbon system and do reaction of isomerization, for example, to this guy or to this guy. So you're making several of these conjugated systems. And so this reaction ID, and this is the error. So the error of our parental omega B97X is ridiculous. It's a disaster. So it can be as high as 20 to 40 kcal per mole. That was, Marcus was showing. So this is extreme. It is a terrible error. However, and basically our neural network trained on DFT data obviously, have this error, so it mimics this behavior. However, the network's been essentially fine-tuned on couple cluster data. These errors are substantially reduced to 1 or 2 kcal. And so the error of our approximation again is the same order. And in the paper we show a couple of other benchmarks. However, I'm short on time. So what also interesting, we also interested in drug discovery and reliable generation of three-dimensional conformers for molecules. So is a nice paper by a Genentech group that analyze accuracy of different methods from the force fields, DFT, and some of the post-Hartwig methods for the accuracy of the dihedral profile when you rotate some group around the bone. So what we show and then so we took this benchmark data set to see what's the accuracy of our methods. So the ANI been trained on the DFT data. See it's here. Basically, it's better than any of the standard state-of-the-art force fields, but it trails the DFT. So with this a little bit couple cluster data, basically the ANI CCX, it exceeds accuracy of all the functionals that's been. This one, it's a good question. It's one really weird system. I'll show you. I'll show you an example. It's really weird. The combination of atoms that makes this the dihedral angle. So basically, and in this paper they tested a bunch of different functionals, and I show just a couple of here. Basically, what we are able to achieve. So the accuracy of this potential is better than any of in DFT in the training, and basically trails this very expensive amplitude couple cluster methods. Now, what can we do and go beyond the simple fit into energies? Now we can combine all these pieces together, and for example, we can do a multimodal training. So we can train at the same time to energies and charges and all other properties you can imagine. And so this paper is currently under review, but it's available on ChemArchive preprint. So basically, we were rethinking the architecture of the neural network, and and be able to add these different modules and different features, and also training on the multiple properties at the same time. So what's interesting is it allows you to do and get the same accuracy of the energy and forces, but also all these properties at the same time. So you're not gaining any, you're not losing anything, but in return, what you get all of them in one shot. So you dramatically accelerate, availability of all the properties in one shot. And we also were thinking about the iterative block in this neural network, which essentially effectively passes messages between different neighbors. And it allows you to still keep our local, feature descriptor, but pass this long-range information. That's been actually a problem for some of these methods. And so to illustrate that, so the T is this number of iteration. And basically, as you increase, the number of iteration, you actually gain in accuracy. And it converges at the step of 3 because of the sizes of our molecules are not very large. But essentially, I can probably skip again. So to illustrate why it's important, you can think about this, the kind of toy system when you have sulfur, which is conjugated, and you modulate different electron donating or withdrawing group here. So if this group is farther than the cutoff of your geometric descriptor, essentially all neural nets would, with the local descriptor, would predict the charge on the sulfur to be exactly the same, because this substituent is beyond the cutoff. However, with the iterative scheme, essentially, you pass this information beyond the cutoff, and basically you can quantitatively reproduce the correct quantum mechanical behavior. What is also interesting, this architecture allows you easily add different properties. So, for example, it's been trained to ground state energies and gas and charges. So we are thinking, can we add more properties and train more efficiently? And we are thinking to do prediction of the implicit solvent effect, because the charges, the atomic volumes, that's those pieces that are important for implicit solvent. So you trivially just add this extra neural net to predict the solvation energy. Again, we use SMD with the same DFT functional, and given only 5% of the total data set, you can train SMD to the same energy error, about 1 kcal per mole. However, the solvation-free energy can be measured, and there is a MNSOL database been maintained by at the University of Minnesota that has extensive number of Gibbs free energy of solvation for drug-like molecules, and none of these molecules in our training data. And basically, we get the RMSE 1.8 kcal per mole, and very nice R square. And this the experimental versus predicted. And here you keep in mind, so we calculated everything with machine learning you calculate the frequency and the thermal correction, everything done with the neural network. And basically this error 1.8, it's about the same as between a couple of different functionals or different approximation to the continuum solvent. So this is as good as it can go. Now, just to conclude, what I think we're going to, see, next year, it's really exciting. So when these methods, we've been actively developing. So now I think it's a prime time to show that we can really do new science and, solve the problems. And just to show you a couple of examples, what we can do even now. So we can take my neural network potential, been trained on a small organic molecules. I can go to PDB, take the protein with a ligand. We cannot do ions yet, but I can put my protein into the distilled water. So this is distilled, and put the periodic box, and so total system size at 35,000 atoms. And again, we have 7 elements parameterized so far. We can run the simulation with explicit water, periodic boundary conditions. And what you see is really boring movie, which is great, because what potential is essentially doing doesn't disintegrate the protein, doesn't explode. So you still see the secondary structure, the ligand where it should be. So at least qualitatively, it learns enough about the protein wants to be folded. And what's interesting is during this simulation, what the student did a trivial mistake. It was automatically protonated. So what happens, you see this this arginine was deprotonated, and so there's a carboxylic group that was protonated, which is totally wrong and under physiological conditions, because this acidic end. But what happened during the simulation, essentially you see the proton transfers. Because those potentials are fully reactive, we can be a little bit more forgiving. And you can basically, it allows you to do realistic simulation with the pH changes. This is a really huge problem for the classical force fields. Finally, let me close with even more fascinating examples. When what we did, we go and we simulate this hot carbon vapor. So it's 4,000 atoms of hot carbon, 2,500 degrees, again, 60 atom periodic box, a high temperature simulation. You start from random gas. What you see, formation of the graphene flakes. There is a formation of the fullerene. You see the buckyball here. And then some of these flakes goes to larger nanotubes. And again, this is the same potential without explicit retraining for this case. What it shows you is that it learns enough to understand that carbon wants to be conjugated 6-membered rings. Those results probably quantitatively wrong, but at least there is a hope that some physics is captured there. So with that, let me leave you with that. So if you're interested, we have the it's all in GitHub. So we have the connector to the ASC atomic simulation environment. We have implementation on PyTorch, and all the data is available to anyone who want to try. Thank you.
Thank you very much. We have time for a question. Yes.
No, not yet. Metals are, because for the metals you need a spin, depending on spin state. Well, in principle, yes. So if someone would compute those charges, we can trivially train. But at this, it's just organic standard. Yes, for QM charges.
One more question.
Yeah, sometimes it's terrible.
So the question, if we repeat it.
Yeah, okay, so the question was, did we make an estimate about the accuracy in the bulk phase, right, simulation? Oh, it's quite, yeah, so uncertainty is quite high, yeah. So you see that's really some of the data is, some of this phase space is underfitted. So we can think about the training to some, condensed phase data, for example, carbon or even pieces of clusters to account for that.
Thank you very much. We should proceed. The next speaker is from the University of Cambridge in the UK. It's Professor Lucy Colwell, and she will present on machine learning with deep feature graphs leads to interpretable models that predicts reaction performance. I hope that was correct. So please.
nice arrangement. That means I can spend a year working at Google and then take the skills back to the university. And as a consequence of this new Google affiliation, I have updated the cover slide of my talk to reflect some of the equipment that we have available at Google. So these are these new TPU pods, which are extremely fast at carrying out calculations. And I also have given this broader title, Accelerating Science Discovery with Machine Learning. Oh yeah, can you not hear me? Oh, thanks. Oh yeah. Is it good? Can people hear? Yes, good, thank you very much. Okay, so I actually have promised that I will advertise a little bit about science at Google at the start of my talk. So I am on this Google Accelerated Science team, which I believe Anatol in particular has worked with extensively. But they're basically a team where the goal is to increase the rate of science discovery using Google technologies. The idea is to partner with experts in various fields across physics, chemistry, biology, and beyond, and to try and use some of the tools that are developed at Google to make impact in science. And so there are some links here that describe a bit of the work that has come from this group. And the reason that I'm talking about this is that we're anxious to recruit interns. So if anyone is doing a PhD or a postdoc and would like to be an intern, we currently have this advert out. Please, have a look at it. Think about applying. If you just Google, this link is ridiculous. So if you just Google research intern, then you will find this advert, essentially. It's like the second hit or something. And we also have this AI residency program. It's like a one-year program. It's a bit like a postdoc. So you can come and spend a year at Google and join the research projects and then go on and do something else. And so most people have a strong AI background, but we also have people who are scientists who are really trained in science, who are sort of learning some of these techniques during the 12 months that they spend there. And so this link here has all the information if anybody is interested. So I'm going to talk first briefly actually a bit about protein ligand binding, just because I want to connect this to some of the neural network work that we heard about previously. So when I went to Google, I got very interested in some of these deep neural networks they have built to predict protein ligand binding. So this was sort of the approach before people made these end-to-end differentiable models. So you have your molecule here, and then you have some kind of featurization algorithm. So you turn your molecule into a descriptor, like a fingerprint or something along those lines. Perhaps it starts from the 2D structure or the 3D structure, or even just which atoms are present, right? And then once you have that feature vector, you then build That would be better. Is that work? Does it work? It's on. It has a green light. I mean, yeah? No, it's okay. I think it works. It works. Okay, great. All right, I'll hold it. We'll give you something to hold. Okay, so this is how people did things before. Of course, we had a revolution in building models and images where people used to use handcrafted features, which they spent a lot of time working on, and they've since moved to these deep neural networks, which you can train end-to-end and which learn the features themselves. And so people, of course, have translated this idea to the space of small molecules, where you simply learn the representation as part of the machine learning algorithm. And so the group that I joined at Google developed these graph convolutions, or was one of the first groups to publish these graph convolutions. So it was a neural network architecture designed specifically for molecules, and you just put in the atoms and bond, and the idea was that you can iterate this sort of weave module an arbitrary number of times to learn complex functions of chemical neighborhoods. And that was subsequently rephrased, in a sense, as a message passing neural network. So there were these exciting sort of advances in the architectures that people use to build networks of molecules. And these were particularly sort of demonstrated in the application of protein ligand binding. Right? So we have this nice protein structure here. This is a beta-2 adrenergic receptor. We know some set of ligands that bind to this protein, and we'd like to build a model that will predict what other ligands will bind to that receptor. And it turns out that these models perform really well. So this is a table in this paper in 2016. These are essentially 3 data sets that people looked at, and the first 3 lines of this table are sort of traditional models. So we have like logistic regression and random forest, and this maximum similarity. And then we have the sort of baseline, which were neural networks built on fingerprints. And then these were these new architecture neural networks built directly on the graph. And I think the takeaway here is that, in general, the neural networks are able to outperform the original models, at least to some extent, right? They're looking good. I wouldn't say it was like a clear win in any sense, but the AUC is, in general, better. So that's great, right? We can build these really deep neural networks on these data sets. We split them into train and test data sets, and they can predict well on the test data. But we might want to ask, what do these models really learn? Right? Like, as a chemist, it would be really nice if we could actually sort of examine these models and ask them why they're making the prediction that they do. I'd really like to know what the pharmacophores are. Why does this molecule bind to this protein receptor? Can you tell me? And can I then use that knowledge to design a better binder, a better ligand? Right? If I want to do lead optimization or any of these sort of tasks, I really need to know how to move in the space, and so I need to be able to examine the network. And of course, people have addressed this question in many contexts, in particular in sort of image analysis, and they developed attribution techniques in order to discover or try and examine what the network's learning. And so we'd like to use that in the context of protein ligand binding, right? So we can figure out what the pharmacophores are. Now, I think it's fair to say that to apply attribution methods and to be able to really judge them, right, we need data sets where we know what the answer is, right? We need to know why the ligand binds to the receptor. Otherwise, if we have too many unknowns here, if we don't really know what the answer is, then we don't know if, the attribution method works properly, and we don't know if the network learned the right thing. And of course, for most proteins, we don't know that answer, right? That's like the $1 million question. If we knew that, we'd be in better shape. So we decided that what we would do is we would simply construct some data sets in which it was like a sort of fictitious, imaginary protein receptor, and we would say that a ligand bound to it if it had a certain combination of fragments present in its molecular graph. Okay, so this sounds kind of crazy, right? We're making toy data sets, but the key thing is that then we would know what the answer was for that data. And so these are the fragments that we considered with their smile strings, and there's a little sort of diagram representing them. And these are the logics that we came up with. There's 16 logics here, and they kind of get increasingly more complex as you go down the table. So they're very simple to start off with. Simply, you have to have no primary amine, and in that case, you can bind this protein. But by the time you get down to the end, it's getting quite complicated, right? There are sort of multiple clauses in this logic, and so we're really starting to get close, perhaps, to what real proteins are like. And so we're going to use each of these logics to scan the zinc database to identify ligands that do or don't bind the protein. So we're just constructing a fake data set here. So we have 16 fake data sets with positives and negatives, right? And there's always data set bias. That's a big issue in chemistry. So we're going to be very careful to balance our synthetic data sets. We're going to sample equally from all combinations of negations of the functional groups that make up each logic. So we tried really hard to make this as balanced as possible. Right? We wanted this to be an ideal case. And we're going to sample 1,200 molecules for each combination, which meant that we end up with really quite large data sets. So we have all of this data, and we train models on these data sets. There's 16 data sets. We're going to train both graph convolutional models and MPNN models. And turns out that, as you might expect, this is quite an easy task, right? These data sets are beautifully clean. There's no noise. It's very simple. Ligand either binds or it doesn't bind. And so the neural networks do really well at this task, right? They get 1.0 AUC or very close to it for every single one of the data sets that we tried. So that's great. We have a whole load of really well-trained neural networks, and we can now examine whether they learnt the correct logic or not. And so to do that, we're going to invent a quantitative attribution method where we use integrated gradients, which is one of the techniques that has been published recently, to calculate an attribution score for each atom in the input molecule. And so there's a little example here where I've sort of numbered the atoms, and so here are the indices, and here was the score that the attribution method gave them. Right? So in this case, it seems like this ring here was really important, or at least the model thinks it's really important, and so it's given it a lot of weight, whereas it's sort of ignored most of the rest of the molecule. And as it turns out, in the logic that we used, that ring was important, so those atoms all got a label of 1, and the other atoms got a label of 0. So this was really perfectly classified. All we ask is that the ones, the atoms that had a 1 label, get higher scores than the atoms that get a 0 label. And so we can literally compute an attribution AUC using these rankings. So we can do this for all the models we've trained in our 16 data sets. We can report the attribution AUC in this table. And for the simple logics, everything's pretty good, right? Like the model appears to learn the correct thing. But as the logic gets more complicated, even in this case where we have like perfectly clean data without any experimental error or anything, we're really starting to have issues with what exactly the model is learning. So at this point, it could either be that the attribution is wrong or the model has learned the wrong thing, right? So we need to try and distinguish between these two cases. And we don't really have a great way of distinguishing these cases. But what we can do is try and exploit the attributions to find adversarial attacks. Right? Now, if we can do this, it suggests the attributions are correct. Right? So essentially, we take this particular example. So we have a binder, and the model correctly predicts that it binds. It says that probability of binding is 0.97. And so when I say binds, I mean it satisfies this logic. Right? So it has this correct combination of fragments. But the attributions are sort of a bit funny. Right? Like there's quite a lot of attribution on these features here, which are not at all included in my logic. And so perhaps that means that I can perturb this molecule so it still satisfies the logic, but the model gets it wrong. And indeed that's the case, right? So I can simply just add an extra carbon into that side chain next to the primary amine, and lo and behold, the model is now predicting that it doesn't bind anymore, even though it does. So I can use these attributions, I can exploit them to fool the classifier, which suggests that the attributions are correct and the model is actually learning the wrong thing. And so I suppose what this means is that the model is learning some signal that correlates with the binding logic, but isn't actually the binding logic itself. And it sort of suggests that perhaps you can construct a test. So if you have some hypothesis and you have a data set, right, you can actually kind of ask whether the data set contains enough information to really test that hypothesis, or whether you need to augment your data set or you know, aim for a simpler model or regularize or so on and so forth. And so we hope that that will be sort of constructive, because otherwise it seems like a sort of disappointing result, honestly. I'd hoped it would be possible to do a better job than we could. So I now want to talk about what I said I was going to talk about in my title, which is essentially using large data sets. They're sort of large. They're not really large enough, and that was why I put that previous example in as a sort of warning that if your data sets are not large, you need to be careful. But we'd like to predict reaction outcomes. So I have some colleagues in the department at Cambridge who developed this high-throughput quantitative experimental platform by which they can carry out many reactions and quantitatively measure the output. Right? So you have this large plate, like a 384-well plate. You put many combinations of components into these wells and then leave it for 12 hours and use something like mass spec or LCMS in this case to measure how much of your reaction product you obtained. And so we started off by looking at a Chan-Lam coupling reaction. We'd really like to be able to optimize this reaction. It's useful for making CN bonds and pharmaceutically relevant compounds. And so we wanted to ask, given a new boronic ester, so that's this piece here, if we have a different R group, different molecule here, can we predict the reaction outcome, and can we propose a catalyst and a base that will give optimal yield? this is sort of a combinatorial situation, right? There are many boronic esters, many catalysts, many bases, and in fact, there's also ligands that we can put into this reaction to try and make it better. And we'd like to be able to train a model that tells us how to run a particular reaction. And so when I say combinatorial, there's many options for each piece. In this case, we kept the amine the same, but we tried many boronic esters, 6 copper catalysts, and 7 bases. And so the problem is that even though we were running these reactions on 384 well plates, there's so many components here that actually the number of unique combinations is quite large. And so even though we ended up with a lot of data, we actually somehow there's many hypotheses being tested. And so we're actually in a sort of low data regime, which makes things difficult. But essentially, we just want to find that we can write the yield as some function of the input molecules, right? Well, that function could be like a random forest, like some model, some black box model, or whatever happens to work well. So this is work that was really done by a postdoc in my group called Carl Polking. We came up with a number of features of the molecules that we felt would be relevant for this reaction. Essentially, because we have little amount of data, we want to encode as much information that we know about physics or about chemistry into the model. And so we sort of thought about using structural features, but we really ended up focusing on these physio-chemical features. So properties of these molecules that we could calculate, typically using sort of quantum calculations, and also some that we measured. So we actually put in some measured NMR data. And the choice of these descriptors is obviously really important. And so the idea was to sort of think about the reaction mechanism to suggest important features. Essentially, the problem with this case is that we really just don't have enough data, which sort of makes things tricky. But there was a paper that was published recently in Science that tackled a similar problem. They looked at the Buchwald Hartwig cross-coupling reaction. And again, they had sort of many versions of each component, and they parameterized them using physicochemical descriptors. So when this paper came out, we were like, oh, okay, somebody else had the same idea. At least we're not being completely crazy. But this paper actually makes a really interesting point, because they take all of their data, right? So they've combined all of these different catalysts and components, and they've carried out all these experiments, and they simply make a 30-70 random split of the data, and they use that to build a model. And the problem is that if you split your data randomly, right, then the chances are that every component will be seen in the training set. Not every combination will be seen in the training set, but every component will be seen, right? And that means that you can make a prediction for a component just by kind of transferring knowledge, right? Like if I have this component in one combination, then I can sort of just predict that it will be roughly the same as in another combination, right? So you have to be really careful with how you do the splits. And I think that's shown by the fact that if you use these physicochemical descriptors, you get a very nice plot. Here are the black dots are the training data and the blue dots are the test data. But if you use a structural descriptor, you get pretty much the same performance, but it seems that should know less about what happens. And more to the point, actually, if you just use labels, if you don't tell it anything about chemistry at all, right, then you still get really what's pretty reasonable performance, right? So when you carry out these splits, you have to be really careful. And this is just the sort of way that we did this label-only prediction. Essentially, we just, if you change the x1, we just use the terms belonging to the other components to make the prediction. We just left the x1 out. And you can do this well without even considering it. So there's like a lot of information leakage here. You have to be really careful. So this is, I think, an example of combinatorial bias, right? So you predict the outcome of a new molecular combination just by sort of tracing subsets back to the ones you've already seen. So how can you get around this? Well, essentially, because we had so little data, we ended up having to invent a sort of molecular term decomposition. Wow, I'm really doing well here with the logistics. So essentially, we just sort of make an expansion where we take this effective Gibbs energy. This is, we're writing the yield of this equation, and we just write it out as you normally would, expand it with sort of single body terms and then pair terms, and then we just expand the exponentials, assuming that things are small. So there's nothing particularly original here, but essentially we're saying that perhaps you can write the total yield as individual terms from the component, and there are some second order terms which we might be able to infer if we're really lucky, right? So then we can sort of figure out the effect caused by adding a new component just by sort of handling the data carefully. So once we've done all that, we need to learn these terms from the data. So if I'm interested in the Brownic ester in particular, I'm going to take the partial yield, which is just caused by that Brownic ester, and I'm going to try and regress it against the data. And because I have so little data, I'm actually going to use a sort of functional regression approach, right? Where I'm going to construct a graph of single variable and paired variable terms. And I'm going to use that graph to explore a space of nonlinear functions to find a functional form of the input descriptors that correlates well with the training data. And this is really dangerous, right? I have very little data, and I'm allowing myself to have nonlinear functions. So like, I'm guaranteed to get really good correlations, right? Because if I try enough things, of course I'm going to get a really good correlation. So I have to be really careful about the statistics. And so essentially we use what we call a random physics-based null distribution, where we sort of swizzle all of the columns of the input descriptors, and then we recalculate everything. And we recalculate everything very many times using sort of bootstraps so that we can get a good null distribution. Essentially, we're using sure independent screening, which people have used before, I think, in materials, in order to give ourselves a strong null. And so we're asking that things really sort of leak out beyond the null distributions. There are lots of statistics here, which I'm not going to go through. But essentially, we end up with functions for those those molecular terms. And it's sort of interesting. I don't think we can really say that these functions are the right answer in any sense, but it seems that they correlate well with the right answer, right? And it means that we're writing like an equation for the predicted outcome of a reaction in terms of the input molecules. And I suppose, so I should also admit at this point that I'm like a mathematician by training. So it's unclear to me why it's not possible to do this in chemistry. So maybe this is, yeah. So it seems to me you should be able to write equations for reactions. Of course, these equations are not unique. This is the function that happened to correlate the best. But we put in physio-chemical descriptors, they all correlate with each other, right? So there are many other things that could have been there. And so we tried to, to give an impression of that with these visualizations, where essentially we're trying to ask, what are the things that correlate the most from the input descriptors? These are all very physio-chemical properties. And you can sort of see that there are areas of these graphs where things all have strong colored lines, and the strong colored lines imply that they correlate quite heavily. And that just means that instead of this particular functional form, it could have been something else that correlates highly with that functional form, right? So these equations aren't unique, but they are at least equations. And what's interesting is that they do quite a lot better than the best conventional model that we came up with. So here we're using a random forest. These plots are all leave compound out plots. So we've taken all the data, say one compound, taken it out, put it in the test set. So we've built a model using the other compounds and made a prediction for this remaining compound. And so they're not beautiful, the plots, the ones at the top. They are better than the random forest plots. And I guess, given the amount of data we had, we're, relieved that we could get something that was interesting. So that was the Buchwald Hartwig reaction. This is the Chan-Lam reaction that our collaborators generated data for. And that's pretty much all I have to say. Or maybe what I could say in conclusion is that we have to worry a lot about bias, in particular when data sets are small. Well, actually, also, I guess the first example showed we have to worry about bias even when we seem to have plenty of data. And what we found is that the statistical filtering gave us sparse, although approximate solutions. We also were able to get confidence limits, which we think is kind of interesting. And we're keen to sort of examine this if there ever is going to be a case where we have too much data. It'll be interesting. I actually have another example for an asymmetric hydrogenation reaction I can show you where we're able to make a nice prediction out of sample. But I didn't really have enough time even to do this. And yeah, even if attribution is possible, we also, of course, have to do interpretation, right? So I guess this is suggesting that all of this AI is really great, but if we want to actually think through the meaning of the functions that we've implied, we still have to have a human in the loop. Thanks very much for listening.
Time for 1 or 2 questions.
Uh-huh. Yes. 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 So you're saying that because, all of the data that I showed you, well, I guess at least the second half of the talk, kind of had must have been full of noise, right? There's noise everywhere. And we could estimate the noise. I think it was like 10% or something, essentially, the noise in the measurements. It's really large. We can deal with this by, adding more points where we draw the outcome from the distribution that we suspect is a noise distribution. We can try and do this kind of thing. I don't know. For me, it was a shock in the first example that even when we don't have any noise, right, there really wasn't any noise, that should have worked, right? We couldn't get it to work. So, or rather, these neural networks will learn anything, right? Like anything that looks like, signal that works, that's what they'll learn. They're lazy, essentially. So I think for me, that was really surprising. We were expecting that to be true. It was an intern project, I should confess. It was a project we gave to an intern, right? And like all good intern projects, the poor person doing it couldn't get it to work. And we were like, well, come on. Yeah, and then we realized that actually it just doesn't work. It's not that simple. So yeah, it took a bit of time to sort of push through. Obviously, the QM case is also really nice, where you have essentially noise-free or very little noise in the data. But I don't know, have people really done attribution on the quantum mechanical neural networks? Uh-huh. No, but I mean for the neural network, right? So you train the neural network on the quantum mechanical data, right? And then it predicts, but like, I just don't know if anyone has done this. It's just if we want them to extrapolate, right, then you sort of have to have them hope that they predict for the right reason. Maybe. No?
We need to proceed with the schedule, and we can thank the speaker again. The final speaker before coffee will be Professor Koji Tsuda from the University of Tokyo in Japan, who will present about machine learning algorithms for designing metamaterials.
Okay. Yes. That's cool. What?
Yes, do it.
Yeah,
this.
like cables. Okay. Good. Okay. Okay, thanks for introduction. My name is Koji Tsuda from Tokyo, and actually I have positions at Nimsan Ranking as well, and I'd like to talk about how to use machine learning to design materials. And I'm actually a computer scientist, so I'm not so familiar with physics and chemistry, and but in this, I don't know, 5 years, I have been collaborating with a lot of material scientists to create new materials. And what I have been doing is automatic materials design. And I use actually machine learning to drive simulation and experiments to come up with new materials. Right? And basically, machine learning is what machine learning does is experimental design. So basically, when you have large candidates of materials, then what you would do normally is to apply simulation to all of candidates and come up with good ones, or do experiments and come up with good ones, right? And what I do here is to somehow to let machine learning choose experiment candidates, and then do simulation and get data out of it, and then use this data to do further machine learning and go on around and around. And for this simulation, we are frequently using quantum mechanical methods like DFTs. So my talk is organized this way. So first of all, I will present Bayesian optimization algorithm. This is a machine learning algorithm, which we use quite often. And actually, for solid-state materials, I present two of recent work, and one is design of silicon germanium nanostructures published last year, and this is basically simulation only study. We used only simulations only, and in the next topic I will present our new work about wavelength selective thermal radiator design, and then we actually designed such kind of layered materials to come up with new thermal radiator, and here we did experiments as well. So we really fabricated, like generated materials and evaluated. And if time allows, I will mention about our protein design project as well. Okay. So what is Bayesian optimization? Actually, Bayesian optimization is a technique to find best data points with minimum number of observations. Yeah, I mean, I will explain later about it. And what you do effectively is that suppose you did n experiments, and then you have to choose the next experiment. So which candidate to choose for next experiment. So this is exactly Bayesian optimization can solve. So Bayesian optimization choose next point to observe to discover the best ones as early as possible. And then we use actually machine learning models to do that. Okay. And first of all, let's see what you do without machine learning. So if you don't use Bayesian optimization, what you do is as follows. So this is screening by first principles calculations alone. And suppose you have a lot of materials, material candidates in the database. And to choose, for example, the best one among these candidates, what you do is to apply first principles calculations like DFTs to compute some properties of materials, and then you have some scores for all of them, and then you choose the best scores material. I mean, there's no problem about this, but one thing is it takes time. So if you apply, if you have only 10 of them, it's okay, but if you have a really large number of candidates, then it takes too much time. So what Bayesian optimization do is, first of all, you just pick up several things and then apply simulator first. So like this, and then next you take this as training data and train a Bayesian model, and then what you can do is to predict score for the rest of your candidates, like this, like predict the score 4 to predict the score 10. And what's important here is that you also compute variances of these predicted scores. And it means that so if you have large variance for your score, then it means that this is not so confident. So you are not confident about your prediction here. And if your variance is very small, then you can say that your prediction should be very accurate. And based on this information you choose the next one to do simulation like this. So in this case, you choose this 8. And the one important thing is it's not just, so in this decision, I looked both score and variance, right? So it's very important to take into account this kind of uncertainty. And then you do the next step, and then go, and then repeat this again and again, and then you can design your experiments sequentially like this. Okay. And I said you choose the candidates, considering score and variance, right? And then I will explain how you do this. And suppose, this x-axis is some explanatory variable for your candidates. And suppose you did 10 experiments already, and you measured some value already, like this. And suppose upper is better, so larger is better. Then the current maximum one, currently based experiment is this. And the question for you is to so actually we have 4 candidates yet to do experiment, and then the question is, well, which one you choose. And in Bayesian optimization, what you do is to apply some Bayesian model. And in this case, we apply the Gaussian process to this data, and then you get something like this. Actually, I apply the Gaussian process to this data, and this red line is just regression function, and this blue one shows your variance of this function, right? Or standard deviation. And then you choose the next one to observe from these 4 according to probability of improvement. Actually, probability of improvement is defined as a probability of getting beyond the current maximum. And if you look at these 4 points, then this one has the largest probability of improvement, because the probability of getting beyond this is like more than 0.5, so it's the best. So you choose this one for next experiment. And after you do experiment here, you never know where is the next measurement. It may be very bad or maybe very good. But anyway, you retrain Gaussian process with 1 extra data, and then you do the same thing again. Okay, we apply this technique to the following problem of ROE structure optimization. And this problem is a bit interesting one. And suppose you have this kind of material with silicon leads. So this white one is silicon atoms. And in the middle, you have this silicon germanium array region. And you have like 16 positions. And you can put 8 silicon and 8 germanium as you like. And your purpose is to maximize or minimize the thermal conductance from here to here. Right. And the number of possibilities here is this. So basically, this is 16 choose 8. So this is Japanese way of writing 16 to 8. But anyway, and you have like more than 10,000, 12,000 candidates. So if you just do some calculation to compute thermal conductance for all of them, it's great. It's okay. But we don't do this, and we accelerate this process by using Bayesian optimization. And to define Gaussian process, you need some kind of descriptor. So you have to represent your candidates as a set of values, right? And in this case, we are using very simple descriptors. And so this 1 to 16 is represent positions, and you put 1 if if it is germanium, and you put 0 if it is silicon. So that's it. And for calculation, we use this atomistic Green's function method, and but actually this part is done by my collaborator, and I was doing this Bayesian optimization. And this is the result. And basically, the left-hand side is represents the result for silicon leads, and the right-hand side you have like silicon germanium leads. And this panel shows how Bayesian optimization worked. And this x-axis is number of calculated structures, and the y-axis shows the thermal conductance, the best thermal conductance obtained so far. And then what you can see is after several hundred trials, after several hundred computations, you could get optimal ones, right? And on average, you could get optimal structures using only 3.4% of all candidates. And when you look at the result, so this is a result for maximum thermal conductivity. And when you look at it, it's kind of regular. So here you have 8 germanium on the top and 8 L silicon at the bottom and so on. But when you look at this minimum case, this is quite complicated. So so basically you have this interface between silicon and germanium like this. And actually the width of each one is not uniform. So it's a periodic structure, and it's very irregular structure, which resulted in the best structure. So this is very interesting from physics point of view. And actually, when you look at our paper, we have a lot of discussions about why it is the case. But what I can do from AI perspective is that this kind of structure is very hard to design by humans because it's aperiodic and it's very hard to predict. And we did similar stuff for superlattices, and in this case you have layers. You have 10 layers in this case, and you can put 5 germanium here and 5 silicon here, and we use the same descriptors. And the best structure for minimum thermal conductivity is something like this, like 1101, 01, 0001. So this is also very complex and aperiodic. Okay. So maybe I cannot really go to. How do I go to videos? Sorry. Okay, maybe I can skip video. Did they want to see the video? Maybe I have to. Don't know how to do this. What? Okay. Oh, it doesn't appear. Sorry, I just. Well, does it? Oh, here. So if I move out, then it doesn't appear. Okay. But yeah, so sorry for this small thing, but yeah. So this is just to explain the current what I explained in this. And first, so you have huge number of candidates, and then you just, so in the beginning you just randomly sample these from these candidates, and so actually for chosen structure you compute thermal conductance using simulator, and and actually by, so this is just image, but so you use Gaussian process model to somehow to come up with the best structure. So this is what yeah, I mean, this is a video that our funding agency made. Okay. So okay. Yeah. So then I move on to this wavelength selective thermal radiator design. And actually, thermal radiator is a material that if you give heat, then it emits light. So basically, that's it. But these wavelengths, selective ones, emit light with a certain wavelengths. Right? And it has applications together with solar cells like this, and maybe heater for drying. But my favorite application is this sky radiator. That so this one emits lights with wavelengths which is not absorbed into air. So then it means that when you give some heat to this material, then the light goes through to the space, so you can cool the Earth. So that's really like science fiction, but it might it's very attractive. And what we do is to design this kind of layered material to this purpose. Okay. And we design this kind of material, and in this case, we use 18 layers, and you fill each layer by silicon, germanium silicon or silica, and we also control total thickness between 3.6 nanometer to 4.6 nanometer, and then we took 21 grid points between these two this range. And then the number of candidate structures is huge. So this number, I mean, I cannot read it, but this number is the number of candidate structures. And what to optimize? What kind of material you want? So basically, we compute. I mean, given some candidate of layered material, we compute emissivity spectra using electromagnetic simulation via transfer matrix method. And this is actually very quick. So it takes less than 1 second to compute in this case. And we optimize the figure of merit by using Bayesian optimization. And you have some target wavelengths here, and you have some range, very narrow range. And we designed our figure of merit to appreciate peaks near target and penalizes peaks outside. And the maximum value is 1. And actually, and when you set the target wavelengths to 6.0 micrometer, and then this is what you get as a final result. And interestingly, silicon was not used. So because, I mean, although we prepared 3 materials, we end up using only 2 materials. And this is how Bayesian optimization worked for different total thickness. And actually we got this after only 168 million calculations. And actually, I would say this because it's only 2% of all possibilities. But actually, one calculation here is very cheap, very short. So we could do this using like 24 days, 24 cores and 24 days. So it's So actually, 24 cores is not at all large. It's only 1 CPU, one Xeon CPU. So 2 Xeon CPU normally one CPU has 12, so 2 CPUs. And we tried 5.0 micrometer and 7.0 micrometer, and you can see slightly different slightly or quite different patterns. But you can also realize different wavelengths. And actually, we fabricated it. So actually, we asked some company to make it, and then this is a calculated spectrum for 5, 6, 7 micrometer, and then in calculation, it's almost perfect. It's really clean and sharp, and then this is the real measurement from our fabricated material. And then when you see this, it's a bit shifted. So 5 is like 5.5 or so. It's a bit shifted, but and the peaks are not so high, but they are still very distinct. And this is a TEM image for 6.0 micrometer case. And the reason that our peaks were a bit shifted is that the width of experimental realization is slightly different, like for example 0.63, 0.69, and so on. I mean, they are approximately right, but it's a bit, yeah. Well, I mean, yeah. So there's some error. And then we actually simulated this width, and then we observed the shift. So if we could manufacture this more accurately, then we could, we could be better. And comparison with existing materials, and actually Q factor is one way of evaluating this kind of material, and essentially this evaluates peak sharpness. And our material achieved Q being 273 for simulation and 188 for realized. And the highest known Q factor for this kind of material is 200, about 200. And it's done by 2D grating, coupled surface phonon polaritons. And one reviewer says that this is not a big deal because you have 200. But it's not so simple. And actually, this material has large unwanted peaks. So if you calculate our peak of merit for this material, it's very, very bad. And our material has very simple structure, just layers. But this one has much more complicated structure. So this has high cost. Okay. So I don't know how much time I have, but not so much. And I will shortly describe our work for designing proteins using Bayesian optimization. And protein engineering is, in short, changing some part of amino acids to get better proteins. But this has a large search space, because if you change k residues, then you have 20 to the power of k possibilities. Okay, maybe I don't have much time, so what we did is to give random mutations to some protein. Actually, in this case, we use GFPs, like green fluorescent proteins, and we made some random mutations. And we used it as a training data, and we learned a Gaussian process from here, and we designed new proteins, and then we measured, and we selected good proteins. And I will show you just a picture. So this is what we did, and this is original GFP, and what we did is to use Bayesian optimization to make it yellow. So we changed the wavelengths of GFP and created really new YFPs, which is yellow fluorescent proteins. Okay. Okay, so this is my conclusion. And actually, maybe you can agree with me that designing layered material is beyond the ability of human intuition. So this is because what I like to to deal with these layered materials because probably humans cannot deal with it. And actually accelerating designing of existing material is of course very variable, but what's more interesting for me is to find a new class of materials which can only be designed by machine learning. Thank you very much.
Do we have any questions for this presentation? Yes?
Chips? May not be, maybe this is saying too much, yeah, probably. But yeah. But actually, I mean, so one pity about this thing is that we started out from 3 materials and we only using 2 materials. And actually, when you use 2 materials, it's not so difficult. But when you say maybe we can go ahead and use like 5 materials or something, then it's extremely hard.
Yeah, sure. Please continue. Yeah, so, well, I mean, we did several analyses, but yeah, well, I can show you our papers. So, I mean, But was the question about the motivation for using silica instead of silicon?
Well, I mean, we used both actually in the beginning, but actually machine learning chose not to use silicon at all. So why? Yeah. So that's a question, and yeah, I'm not a physicist, so I cannot answer. But yeah, and also it's machine learning, so no interpretation. But yeah, but I guess there is some reason for that. Obviously.
All right, let's thank the speakers again.